The paper of the day is Spanner, Google's globally distributed database. Spanner is Google's scalable, multi-version, globally distributed, and synchronously replicated database. It is the first system to distribute data at global scale and support externally consistent distributed transactions. This paper describes how Spanner is structured, its feature set, the rationale underlying various design decisions, and a novel time API that exposes clock uncertainty. This API and its implementation are critical to supporting external consistency and a variety of powerful features, that is, non-blocking reads in the past, lock-free read-only transactions, and atomic schema changes across all of Spanner. Paper first measures Spanner's performance with respect to replication, transaction, and availability. Paper then provides some data on true time behavior and a case study for their client F1, that is ads backend. Looking at the contributions, Spanner combines and extends on ideas from two research communities. From the database community, a familiar, easy-to-use semi-relational interface, transactions, and a SQL-based query language. From the systems community, scalability, atomic sharding, fault tolerance, consistent replication, external consistency, and wide area distribution. One aspect of their design stands out. The linchpin of Spanner's feature set is true time. Paper has shown that reifying clock uncertainty in the true time API makes it possible to build distributed systems with much more stronger time semantics. Here are some of the Spanner facts. So first is, what is a clock? A clock is an oscillator driving a counter. The oscillator should tick at a steady known rate, that is 1 tick per second. The counter must initially be synchronized to a source of the correct time. After that, oscillator ticks cause the counter to advance the time. If the oscillator ticks at precisely the right rate, the counter will advance in precise synchrony with the correct time. In real life, the oscillator ticks at a varying and somewhat incorrect frequency, so the counter gradually drifts away from the correct time. What is atomic clock? A highly stable oscillator. There are two main technologies that go by the name atomic clock: rubidium clocks and cesium clocks. Both exploit changes in the state of outer electron, which involves specific quanta of energy and thus wavelength. One can tune a signal generator to precisely that wavelength by watching how excited the electrons are. An atomic clock is just the oscillator part of a clock. On startup, it must be synchronized somehow to UTC, typically by radio broadcasts such as GPS. What kind of atomic clock does Spanner use? Sadly, the paper doesn't say. Rubidium clocks are typically a few $1,000s, and rubidium clocks drifts by perhaps a few microseconds per week, so they need to be resynchronized to UTC every once in a while. Cesium clocks cost perhaps around $50,000. The HP 5071A is a good example. A cesium clock doesn't drift. Of course, any one clock might fail or suffer a power failure, so even the perfect cesium clocks, you still need more than one and the ability to synchronize to UTC. My guess based on the price is that Spanner uses rubidium clocks that are synchronized with GPS receivers. How does external consistency relate to linearizability and serializability? External consistency seems to be equivalent to linearizability, but applied to entire transactions rather than individual reads and writes. External consistency also seems equivalent to strict serializability, which is serializability with the added constraint that the equivalent serial order must obey the real-time order. The critical property is that if transaction T1 completes and then transaction T2 starts, T2 must see T1's writes. What is external consistency? Why is external consistency desirable? Suppose X changes the password on an account shared by her work group by a web server in a data center in San Jose. She whispers the new password over the cubicle wall to her colleague. Cassandra logs into the account by a web server in a different data center in San Mateo. External consistency guarantees that the Cassandra will observe the change to the password and not, for example, see the stale replica. Could Spanner use Raft rather than Paxos? Yes. At the level of this paper, there is no difference. At the time Spanner was being built, Raft didn't exist, and Google already had a tuned and reliable Paxos implementation. Have a look at the paper Paxos made live by Chandra et al. What is the purpose of Spanner's commit wait? Commit wait ensures that a read-write transaction does not complete until the time in its timestamp is guaranteed to have passed. That means a read-only transaction that starts after the read-write transaction completes is guaranteed to have a higher timestamp and thus to see the read-write transactions right. This helps fulfill the guarantee of external consistency. If T1 completes before T2 starts, T2 will come after T1 in the equivalent serial order, that is T2 will see T1's right. Does anyone use Spanner? It's said that hundred of Google services depends on Spanner. The paper talks about its use by Google's advertising system. Google's Zanzibar authorization system uses Spanner. It's offered as a service to Google's cloud customers in the form of Google Cloud Spanner. The CockroachDB open source database is based on Spanner design.